Welcome to Directed Light's educational video series. We'll be exploring lasers, their applications, and providing you with a number of how-to videos. Please click like and subscribe to our channel to see future videos. Thank you for watching.
Hi, I'm Peter Buzatil. I'm with KUKA North America, and I'm the director for R&D. And what you see around me is our development center. It's our joining lab, and it's focused on high-order joining technologies. In this case, it's lasers. And wanted to talk to you about a little bit of the history of lasers in the automotive industry. First of all, we go back into lasers were developed and actually invented back in the 60s. And right shortly after that, they started being implemented into production. And this is before my time, but I am kind of dating myself here. But back in the 80s and all through the 80s, we had carbon dioxide lasers, which at that time gave us the best benefit, best bang for the buck as far as outlet efficiency. And we actually developed a lot of systems that were welding with robots that had through the arm beam delivery, but those systems were very complicated, and especially at high powers, we had problems keeping them running in production. And shortly after that, we started looking at high-powered YAGs, which had a different wavelength at 1.06, so we could deliver through a fiber optic. And then we started using just generic robots that you see behind me that can be utilized to manipulate the beam through the fiber optic and do the work that we needed to. There were a bunch of companies back then, and you saw the list, but shortly, right at about 1990 and 1993, there were a couple of companies that came out. One of them was Martech, another one that was Hobart, and Lawrence Livermore Labs started developing continuous wave lasers. And with those type of lasers, instead of pulsed YAGs, we can actually process a lot further and better with welding technologies and cutting technologies utilizing robots. So the next slide will show some of that growth that happened and has just exploded within about just at the turn of the century, where we started seeing a lot more CW, continuous wave type YAGs. So if you take a look and see where lasers are utilized today with that involvement, you'll see that we do anything from ablation to heat treating, marking. You'll see the list as it goes on and on. But in general industry to the right that you see there, we can actually utilize not just in automotive industries, but a lot of the feeder applications to automotive utilize this technology in order to process vehicles themselves. So if you take a look at historically where we've been with lasers, in 1972 we started applying them, and it's rather interesting to see how the Americas and in Europe, specifically in Germany and Italy, where we have quite a similar parallel background as far as utilization of high-powered industrial lasers, whether they're CO2, carbon dioxide, gaseous lasers, or solid-state lasers. The throughput and the technology development was actually done in parallel. And you'll take a look and see back in the 70s, or early 70s especially, where we started utilizing this technology for industrial use. So the first application I wanted to talk about was in 1972, Ford wanted to test out this new heat source, this new potentially welding application where they were welding the underbody of this Ford Torino. And it was put together, but back then they realized that the laser isn't the only thing that needs to be accounted for, but the tooling also had to be accounted for. So Although this application went into production, it didn't last too long, mostly because of the gaseous lasers being very hard to keep the beam in alignment and clean at that time, but it proved exactly what needed to be done. It was a developmental system. It did its job. It lasted for 4 years in production, and then it continued on into some of the technologies that we see today. And not only welding, but also cutting. So back in the 80s, we started looking at carbon dioxide lasers once again to cut various option holes into the vehicle. So if there was, in this case, let's say a minivan that needed a luggage rack, it's not every vehicle that needed it. Maybe 17% of the vehicles that were produced needed a luggage rack. In this case, a laser would come in, and instead of having a very expensive die to do that job, we would actually put it in production by demand. Back in the 80s, there was a gentleman by the name of Frank DiPietro, who's nicknamed the grandfather of the laser for automotive purposes. A lot of our mentors today who worked underneath him, he started developing laser systems where he had, at that time, lasers were very, very expensive, where he wanted a system with a robot, a laser, and a chiller all together for about $250,000. That was very ambitious back then. But today, you can get a package even well under that for production purposes, and you're going to see a couple of applications coming up. So also back in the late 80s, when gaseous lasers and solid state lasers started to actually emerge, there was a system that was developed, and it was the radiator support for the Caprice Classic. We learned back then that what this exercise was for was actually to replace resistance spot welding with laser stitches. When we did that, when we actually found what the strength of a resistance spot weld compared to a laser stitch, when we did the pull testing for that, we actually found out that we needed a certain length. When we applied that into the product itself, you see the stitches there around the radiator support. When we did that, that part actually became about 17% stronger than the resistance spot welding one. Actually, and that caused the problem because we actually had to take out, the part became way too stiff. We had to take out resistance spot welds in order to make the part a little more flexible, because we were actually bringing in all the road harmonics through that part and into the hood, and the hood would actually start to flutter at certain speeds. So we started learning that although we were replacing lasers for resistance spot welds, or vice versa, I should say, we had to actually start looking at how we actually built the parts and how we structured the parts. As we progress along in the history of using solid-state YAGs, back in the early 1990s, we developed a system for General Motors at that time where they had a product, a truck or an SUV as well, that required a lot of variability, with about 69 different product variations. What we're talking about are different powertrains, different transmissions, different engines, different seats, seat combinations. They had 6 different seat combinations, about 4 different engines, 6 different powertrains, etc. And what happens is you need a stamping die for each variation. And so what they wanted to do was develop a system to actually customize that product, and we were able to do so. There were 5 different lengths, and that we couldn't change with the laser. So that was the only variability that we had. We would put in a different length for a crew cab, a club cab, etc. for the truck, and then actually customize the rest of it with a fiber optic YAG system. This was offline. When we say offline in the automotive industry, it means that it's not online where if the laser isn't running, you don't produce cars. In this case, what you don't produce is underbodies, because we were customizing the underbody, so we can actually rack or bank the systems up with product and then feed into the line. Back then, a lot of people believed that lasers had a very short lifespan, somewhere around 2 to 3 years. And actually, when we put this product or the system into production, it was 1991. They actually decommissioned it 13 years later, which is a true testament to, even though the technology was still young, we still produced very good quality systems. And now today, we have systems that are running in 10 years, etc. So we go one step further. Once that was developed and understood, in the mid-90s, Ford wanted to do a system where they actually cut and customized the floor pan after the body was built. That is, it's not on the underbody anymore. It's a fully built vehicle. And what happens then is that if the lasers don't work or if they're down, you don't produce cars or trucks, and that's a big problem. So, but we actually, right off the get-go, we had 4 plants, 4 systems in 4 different parts of the country running at 65 jobs an hour. And they were, as a matter of fact, they're still cutting product today. Not in that generation, of course, they've been updated, but we're still doing this today. And then that was cutting. This is welding. This is a very interesting application where we were actually replacing resistance spot welding. This product became 18% stronger than the resistance spot welding application that was preceding it. And we eliminated the weld-through sealer, because when you resistance spot weld, with the distortion and everything else, you have to put a weld-through sealer. But if you do a continuous beam welding with a laser and a robot, you can actually replace all that weld-through sealer. And this was a very good application showing that we can weld galvanized, coated, and uncoated materials. And then lightweighting started coming around, and hoods, etc., and what we call closures, or what they call hang-on parts in Europe. This is a hood application for the LS2000, and we needed to cut a very specific hole that was the largest we can do because of airflow onto the powertrain, and that was set up for towing and Autobahn applications. So we had to cut the largest hole possible, but if you do that with a stamping application, it caused way too much distortion into the part, and it caused way too much distortion, and you could see it on the hood. But with a laser, although it's a thermal application, we were actually able to cut it without any contact, so we were able to do a very good quality job. And that was in production for about 4 years as well. And then ultimately, we produced a whole vehicle, all the parts that you see externally for the Ford Thunderbird. It was a niche market vehicle, was produced with a laser. All the trimming, instead of having trim dies, we were actually able to replace all the trim dies with a couple of laser systems that trimmed all the peripheral offal, what we call binder and offal, off the stamping parts. And that was built on the LS chassis, but everything externally was laser trimmed. Interesting fact is that you can justify the cost of a trim die at about 20 to 25,000 what we call hits a year. That is, you have to have a product that you can sell 20 to 25,000 parts of. But this particular vehicle, they only estimated roughly 20,000, 18,000 vehicles. So it cost justified using a laser system compared to trim dies. We started looking at aluminum applications way back in the mid and late 90s, where we were replacing rivets in this case, self-piercing rivets and pop rivets, commercial pop rivets. And we replaced 92 in this case, in this particular application, 92 rivets with laser stitches. These are all robotic systems. And now today, we start seeing a lot of impact with lightweight and, of course, safety. The pictures that you see here are relative to corporate fuel economy and, of course, the safety. Rollover crush tests have to be performed. So we're dealing with a lot of new exotic high-strength materials, lightweight materials that are high-strength as well. And that's a challenge, and lasers are up to that challenge in most cases. And if next slide, you'll actually see an application where we're using a lot of hollow structures. And if you take a look at that picture with the dotted lines on the electrode there, that's a resistant spot weld application that is very, very typical. Up to about 15, 20 years ago, literally 100% of the vehicles were resistant spot welded together. Now, because of hollow structures that you see there, hollow structures give you a lot more rigidity, strength in a compact form, so you can actually get a lot more visibility, a lot more the doors are actually larger, you can get in and out easier into a vehicle. So you have that, what we call egress and binocular vision in the industry. We're actually counteracting that with smaller sections but high strength capabilities. And we were actually doing that with rollers to actually push the parts onto the supporting parts, the hollow structures, to actually do the welding. So here's a particular application that extends from the what we call the windshield or the A-pillar right over all the way across the roof, and we're attaching the roof and the body side to the substructure of a vehicle. And these are some of the cross sections that you see. They're all hollow sections. So where are we going? What are the trends? Not only in automotive, of course, where we're talking about a lot of aluminum. And aluminum is an interesting application or a product where a lot of people just say aluminum, but aluminum has so many different alloys. There's so many different series of alloys that are used in aluminum that each and every one has its own characteristics. Each series has its own specialty requirements that we have to do. And we have to bring in all kinds of other technologies along with lasers in order to join them. Not only are they automotive, but they're also aerospace. So where do we see lasers now in the body shop? We're starting to see and getting closer to having lasers and regular rivets and resistant spot welding all working in harmony together, and building body shops. We can actually do this through simulation, where we can actually show the productivity ups through various technologies and bring in lasers into production a lot more. So thank you for your time.
Subscribe to our YouTube channel for future episodes of lasers and their applications. Visit directedlight.com for tech tips and information on our line of mission-critical spares and laser field service. Or better yet, give us a call to discuss how we can help you maintain your laser and ensure maximum uptime for your application. Thanks again for watching.